sorry, so I was just explaining that I'm trying to show that, well, that singletons are closed in W. Here's the complement of a singleton in W. If I look at the complement of the singleton within X, I already know that that's open because capital X is T1. So if I take everything in X except for that point little w, that'll be open. And of course, it just turns out that when you intersect that with W, take a look at the picture. If you take everything except little w and you intersect it with all of capital W, you get exactly that shaded region. In other words, this equal sign is correct, right? If I take little w out of big W, it's the same thing as taking little w out of X and then intersecting with W. And the point is, this is an open set in X, intersected with W, so this is in the restricted topology, tau restricted to W. It means that this is open. So the claim is true. Singletons are closed. Okay, fantastic. So we at least know that W is T1. Now I'm going to try to show that W is T3. The definition of T3 with respect to capital X is here, but of course we have to apply it to W. So what I'm going to do is I'm going to let capital F be closed in W, and I'm going to take an element, I'm going to call it little w, that's not in capital F. Okay? And what I have to do is come up with open sets in the subspace topology that have an empty intersection where W is inside of one of them and capital F is inside of the other one. Okay? Now we know already that X is T3. We're going to need to use that, of course. We're trying to show that W is T3, but I already know that X is T3. So if I can find a closed subset of X, for example, and a point outside of it, then we could use this property of T3 for X. That's what we need to be searching for. That's what we would be hoping to do, right? As we think about how can I possibly use the assumption that X is already T3. Well, in order to use that, which you would assume we would need to do, you need to have a closed subset of X. Okay? So the way to get a closed subset of X out of just this bare minimal assumption here is to realize that, well, W minus F is open in W, right? The complement of capital F would be open in W, and anything that is open in W can be written as an open set in X intersected with W. So I'll write it as U intersect W, where U is open in X. In other words, U is in tau. Now this U right here is not the same U that's in the definition over here. Okay, we're going to use the definition in a minute. For right now, I'm just referring to the subspace topology. But look at that. I have an open set in X. So the complement of that would be closed in X. So in other words, X minus U is closed in X. This is what I've been looking for. I've been looking for a closed subset of X. Now let's think about whether W is in or out of that closed subset. Notice that W is not in F, right? So in other words, W lives in the complement of F, right? W lives right here. Well, that means that W, so let me just come over here and make that note. So since W is not in F, W is in the complement of F. Okay, so W is in this intersection, right? W is in U. So W is not in the complement of U relative to X, right? So W is not in that set. All right, great. So not only do we have a closed subset of X, Our point that we started with, this little w, is outside of that closed subset. Okay, so then, since x is T3, there exist, I'm going to call them u prime and v prime in tau, with w an element of u prime, x minus u contained in v prime, and u prime intersect v prime empty. This is what we get from the knowledge that x was T3. Okay? I'm going to just give myself a little bit more room to finish the proof. We're almost done. We're almost done now. I just want to give myself a little more room to finish this argument up. We're just trying to show that w is T3. Okay? I started with a closed subset of w and a point outside of that closed subset. I've got to come up with open sets in w. Now, the u prime and v prime are open in x. But of course, what that means is that then if we intersect them with w, right? If I take u prime and I intersect it with w, or if I take v prime and I intersect it with w, I get open sets in w. I claim that these two sets are going to be our winners. These are the two sets that we're really looking for, right? They're in the topology that we are interested in. Let's check these three things about those two sets. So here are our candidates for demonstrating T3 for W. And I just have to check that they really work. For example, the last part here. So just note that if I take these two sets here and I intersect them, well, I'm just doing a massive intersection here that includes the u prime and the v prime, which are already disjoint, right? There's nothing in common even with u prime and v prime, so you're just going to get the empty set out of that. Okay, so that's good. Let's check and see if our w lives in the first space here. So let's just check that really quickly. Little w, of course it came from capital W, so that part is no problem. Is it in u prime? Oh, it says it right there. Okay, so little w is in u prime intersect w. That's a check as well. Okay, and finally, the last thing we need to note is that our set capital F is a subset of v prime intersect w. Now, capital F is already inside of W from the very beginning here. So we really just need to convince ourselves that capital F is contained within V prime. And this is fairly much clear. I'm going to just draw a picture to kind of show you what's actually going on here. So let me put a picture up here somewhere. This is the last thing I need to prove, and then I'm done. So let's say capital X is like this, and let's just say W is over here on this side of it. Okay, we started off with a closed set capital F. I'm going to put it right there. So W minus F is right here. Notice that W minus F is supposed to be the intersection of U with W. So let's just suppose that U looks like this. Okay, so U is like that. So U is this whole strip right like this, and W is this whole strip like this. And when you intersect them, you get W minus F right there. Right? Just to kind of visually see what's going on. Well, V prime, notice that the complement of U is contained in V prime. The complement of U is this strip right across the top, yeah? That's X minus U all the way across the top here, and F is certainly inside of that, right? F is certainly inside of that strip, and that strip is inside of V prime. So F is inside of V prime as well. Right, so there you go. This note is also true. It is a little bit of a set theory argument to kind of convince yourself of that. So we had to do a little bit of work, but we've shown that a subspace of a regular space is still regular. This would be too much probably to throw at you in the middle of a midterm or something like that, but I do think you should be able to understand every single little piece, every single little step of this argument, and if there's anything that you're in any doubt about, I hope that you'll follow up with me and ask me about it. I'll be happy to kind of go through it again with you in a little more detail. That's it for this session. I appreciate your attention. Hope that you got a lot out of it, and I'll see you guys again very soon. Thanks.